they had retrieved these solid fuel boosters and examined these O-rings, and they found that in some cases there was damage to these O-ring seals. And so what was the cause of this damage? Why was there missions where there was damage, and why were there other missions where there's no damage? And so it turned out that that it was the temperature that was a factor in this. And so we want to investigate if the temperature at launch time has an influence on whether these O-rings are damaged or not. So here's a list of data. We have the temperatures at launch time, and we have the outcome of the whether there's damage to the O-ring seals or not. So here is the first shuttle mission was launched where there was a temperature of 66 degrees and there was no damage. And 70, it was damage, and so on. And so the question is, do these data here, do these tell us something about the connection between temperature and damage to these seals? You see, this is a classification problem. We have two values, damage or no damage, which we label as 0 and 1. And here we have another set of continuous variables, namely we have the temperature. So we view these temperatures as one-dimensional vectors. So we want to investigate whether there is a connection between the damage and the temperature. So this was a thing that was discovered by Richard Feynman. Richard Feynman was a member of this investigating panel, and he did an experiment that showed that this material these O-rings was made of would lose elasticity under low temperature conditions. And I think that in fact that was known to some of the engineers, but they didn't know logistic regression, so they hadn't really done an analysis of the data. But this is Richard Feynman, and this is the thing that he showed, that he dipped this material into some ice water, and he showed that it lost its elasticity. So let's see if we can analyze these data here. So let's try to make a model. So again, we have the temperatures. These are our data vectors. I'm going to turn the zeros into -1, so it's the same as we did before. So -1 here means there's no damage, and +1 means damage here. So this is our data set here. We have the data vectors, we have the labels. So let's see how this is coded. We have the here first sigma is the logistic function. We have the loss function. It's the average of all these things here. So I add a 1 to them, which is what we saw that we had to do, and then I compute here the loss function. So I'm using here a vectorized way of doing this, which speeds up the computation. So I'm not going to go through precisely how this works, but you can think about it and so see if you can figure out what goes on here. But you can also write it as a loop if you want, and just add up the parts of the terms in the loss function. So we have this loss function, and now I'm gonna. This is not so difficult because there are only two parameters here. There's beta0 and beta1 because our data vectors here are one-dimensional. So they're beta0 and beta1 here. So it's beta0 plus t times beta1. That's the z that we had from before. And so we can, in fact, sort of get an idea of what this loss function does here by drawing these level curves here. This is what this heat map here shows what the loss function looks like. So you see here, if we go out here on up here, we're at the value is 34. Down here it's 8. So we can see that it declines here as we go down here. You go down to something here where the color is very light, so that's where we're at the minimum. Then we start going up again. So, but we also see here that there is a valley here in the loss function. So we're probably looking for our minimum down here somewhere in this valley here. But this is a real problem for gradient descent, because once you're down here and you have this long flat valley here, that means the gradient is going to be very close to 0. And so when we subtract a multiple of the gradient, we are going to get very, very slowly going towards the minimum. It will go to the minimum, but it will converge really, really slowly. So that's going to create problems. So let's see what happens here. So we can sort of look at slices of this loss function here. Let's keep beta 0 equal to 1 and vary beta 1 here. So then it becomes a function of one variable, and we can see what happens here. This is what the graph looks like. So we see here we have this sharp drop off, and we end up down here in some valley here. If we go the other way, if we keep beta 1 equal to 0 and let beta 0 vary, then we get something that looks like this. So when we do this means that we are going somewhere along a line here. And so we can see here that we're maybe dropping a little bit, but then we start going up again. So this is supposed to be a horizontal line. But it's a tricky function to minimize. So here's if you want to play with this, these are the graphs here. You can try different values for beta 0. You can put in a different value for beta 0 here, and you can put in a different value for beta 1 here, and try to figure out what these slices look like for different values of beta 0 and beta 1. The gradient, there was this long computation we did, and here I have coded that in. Again, this is done by vectorizing it, so using vector operations to do this, which is a very good way of speeding up computations in Python. So anytime you can vectorize a computation, instead of using loops, you can use vector operations. It runs much faster. So we have our usual gradient descent sequence here. The old value, learning rate, and the gradient here. And we can see what we get. So we run this for 1,000 times, and it does not converge. That's what we can see here, right? You can see here, it does not converge. These values here, they jump up and down, so it doesn't converge. So that's very bad. And it's not so strange. So if we look at a picture here, so remember this slice we looked at, there was this very sharp drop off and this very small value here where it's very, very pointed here. So it is differentiable, but it's a very sharp point here. And so what happens here is that when we take gradients and go from here to here, then the next point would be here. And then we go from this point down here and we end up here. We go from this point, take the gradient, we go down here, and we end up actually further away from the minimum. We're trying to get to here, right? But the way this is going here, we alternate around this. So this is precisely we also talked about this last time. When we have a learning rate that maybe is too big, we might go back and forth around this minimum point we might never get to, and this is what happens here. So let's try to, well, if your gradient descent sequence does not converge, what you're supposed to do is to lower the learning rate. So let's lower the learning rate. Instead of having it to be 1 over 100, 1 over 1000. So now it looks like it's converging. So we get something that looks like this, and this looks like it's converging. In fact, it's not. It is converging, but this is not converging to these numbers here, because as we will see, the minimum is very, very far away from these and from this number here. So we're starting our gradient descent at the point 0, 0. And as it will turn out, the point 0, 0 is very far away from the minimum of this loss function. And so our gradient descent is going to converge extremely slowly. And the reason is we're down in the valley. We get down in the valley very quickly. But once we're down in the valley, it goes very slowly. But if we don't think of that and just say, hey, it's converging. Yeah, these are our minimum values. So we're good. Let's see what we get if we do that. So let's take these values here, beta 0, beta 1, equal to this. And now we try to make predictions. So what was known is that the launch time of the Challenger mission, the temperature was 31 degrees Fahrenheit. So it was below freezing. So this is actually the coldest temperature that they had ever launched at. It was very cold. And but our model says, okay, the beta is here, data point is here, temperature is 31, put in the 1, and let's see what the logistic function gives us with this thing. And we get 0.39, which means that this is less than a half, and so that would mean there should be no damage. So according to our model, it should have been okay. It shouldn't have happened. But of course it did. So our model is not very good. It doesn't predict the right thing. And as I said, the reason is that we have not found the minimum here. This is very far from the minimum. And what happens is that, again, it's because it converges so slowly that we would have to take hundreds of millions of steps in order to get close to the minimum. So let's try to see what goes on here. So again, I try to do some experiments here with fixing a part of the loss function and fixing one of the parameters rather. So if you do that, you can sort of see here. This is when we're at the bottom of the valley, and so you can see how slowly it actually it looks almost like a straight line here. So the gradient is it looks almost like a horizontal line. So the gradient is very close to 0. So if we look at a slightly different scale of it here, you can see that it does the loss function here does decline, and it looks like here is a minimum value around 15. The value we had before was 0.02, and in fact it should be 15. So very, very far from the actual minimum of the loss function. We can see here what goes on here. We can see what. Now here we're close to a beta 0 being 15, and we see the values of the loss function here are much smaller here. So here's 0.44. We're much smaller. Before, when we were around 0, the values were like 2 or so. So we're much closer to the minimum here, and we can see that if we, instead of starting at 0.0, we start at 15.0, then we get convergence towards a minimum point, and that's in fact is the true minimum of this function here. But if we didn't do this analysis, we would end up with a completely wrong model. We would have the parameters would be completely wrong. So This is a learning example that says that you really have to be very careful when you analyze a model, when you try to find the parameters. It is not an easy, it's just not blindly using gradient descent. You're gonna have to be very careful. So let's see what happens if we use these new parameters. So now the beta 0 is 15.02 and beta 1 is minus 0.23.
Yeah, I have
and
a
now,
question.
Yeah, sure. Mm-hmm.
So I was wondering, in the previous slide, when we see that graph where the minimum is at 15, right? So if we look at 0, the slope is still pretty steep, right? So
no, but
if we start
that's because of the scaling here, right? If you look at the scaling here, right? This here the scale is it goes from 0 up to 25. The y-axis here only goes from 0.44 up to 0.60. So that's the reason why it looks like it's much steeper, but it really isn't. So here is a more realistic, where it goes from 0 to 5 here and from 0 to 25 here. So if we were used to the right scale, so we had the same scale here, this would be indistinguishable from a horizontal line here. So you couldn't really see it from a graph like this. That would be very difficult to see where the minimum was. But when you rescale it here, when you scale differently, then you can see it.
Right. Okay. I see. Yeah. Because you have the y-axis change from 0.60 to 0.44.
Right.
Okay.
Right.
Yeah. Avinash has one question. Avinash, you can ask.
Okay. Yeah.
Sorry, I was just asking that this whole problem of being able of guessing, or in some sense applying foresight to whatever the model has produced, and always this fear lurking whether we've reached the minimum or not.
Yeah.
I was wondering, are there ways to stretch a loss function or transform it so that the values become more exaggerated, and thus get a better sort of a view as to where we must search, and then come back and search in the main function again?
Right. I don't think there's a. I mean, we'll see ways of getting a better way of finding the minimum, but I don't think there's sort of a general way of doing it. It's sort of, you just have to be careful and not sort of say as soon as you have found something that looks like it's converting, then you're happy and you go with that. It does underscore the fact that you really have to think carefully about what you're doing and keep testing it out and see the results you have gotten, whether they make sense or not. So it's a warning to always be very careful about what you're doing. I don't think there's any real way, because I mean, in general, you're going to have a very high dimensional loss function, so it's going to be difficult to graph them. But I would definitely recommend graphing some of these slices here and try to get an idea for how the loss function looks. That would be as much as you can, because of course you can't graph it if it's very high dimensional. But try to take slices and see what it looks like. There would be a very,
yeah. I mean, even like graphing will be pretty difficult, because thankfully this data was only two-dimensional, like two-dimensional plane. If we have like a vector of like 10 dimensions, we don't know which direction the valley is and where.
No, that's right. Exactly. That's right. I mean, you can look at the gradient and see if you have a gradient in one of the variables that's very, very small, maybe you have to be careful there. So yeah, I mean, it's a thing. We'll see there are ways to instead of using gradient descent, you can use other methods that'll help you find the minimum. So it is possible to do it. But let's just see what. Yeah, go ahead.
Yeah, so Professor, I mean, I'm just trying to get my head around this. So in this particular example, I mean, we knew the outcome, right? It looks like we were trying to fit the model because we knew the outcome, right? But that's not going to be the case.
That's right.
Yeah.
So how do we?
Well, I mean, one of the things you would try to divide it into you try to take a test set, so keep some of the data out of your training, and then see how it performs in the test set. So what we get here is we see that it performs poorly on we have a test set of 1 data point, but that's because we have such a small data set. But that would be one indication. Take a test set and try to see how well it performs on the test set, and also you can see how well does it actually perform on the training set. How well does it match up with the data you have? There would be if you did that in this case here, you would definitely see that there was a big problem. So if you just looked at how does a model with these parameters we first found, how does that perform on the training set? You'll see it performs really awfully, and so there will definitely be a signal there was something wrong. So that you should always do these tests. I mean, once you've found a value for your parameters, you should always try to see how well does it perform, how well does it fit the training data, how well does it perform on the test set. So these are absolutely essential to do these things, and they would have given you a warning there was something significantly wrong.
Adam, you have a comment?
You should unmute him, otherwise he can't hear.
Sorry.
You just muted me. Now I'm unmuted.
Yeah,
I was just trying to unmute myself. Yeah, I agree with everything Neil said. It's just worth noting that for problems like linear regression and logistic regression, the loss functions are sufficiently easy that there are mathematical techniques. But everything Neil said, is truly true. And when we get to some more complicated techniques, it is a big issue. Did you find a minimum or did you find a local minimum?
Right.
And it's an important area of mathematical research, and it's an important area of research within the machine learning community. When you see my presentation, I'm going to address the issue of how good is this model. So you'll see that, in fact, this was reasonable.
Yeah, I mean, this is not even a local minimum because this is a convex function. So the loss function for logistic regression is a convex function, so it has only one minimum. But it's just not clear where it is, because I mean, if you have this long, narrow valley where all the values are small and it just declines very slowly as you go down the valley, then it's difficult to find the minimum. But as there are ways to do it, and I'll just show, and at the end I'll show a way to find the right thing. But there are other ways that you can do it.
And it's a known problem with gradient descent, and it's one reason why it isn't a panacea. So, I'm going to mute myself now.
Yeah. Okay. All right.
If I can.
Go ahead. Yeah, please.
Sorry, Avinash here. Just another question. Just to strengthen the understanding a little bit, let's say, let us pretend, for example, that we are historical mathematicians and we just know about linear regression, right?
Right.
And then someone poses to us the problem that, hey, do classification for me. With the current reasoning, let me say a few sentences. You tell me if that would be right. So as that mathematician, I would think, well, I already know how to do linear regression. This problem is only different from that problem in the sense that now I have to get my output to split two discrete values or discrete buckets.
All right.
So let me search for a function which tries to, again, now that I know sigmoid, so I'm using that example. So let me use the sigmoid. Would that kind of thinking have gone through the minds of mathematicians at that time, or are there more rigorous ways to, or a different line of reasoning altogether to arrive at the sigmoid and things like that? Because rest of the things are exactly similar as I see them. whether it is your gradient descent.
Yeah, right. There are ways of doing it. You can get what they call the odds of the what can I say, the odds of it of being
The model.
+1. Yeah, well, yeah. So if you do the odds, well, I'm not going to really get into that, but the odds is like log of the sigma minus 1 divided by log of z or something. I'm not quite sure, but that is a variable that's continuous, and so that you can do regression on. If you do that, then you in fact get logistic regression. So it's like the log odds actually. So it's like so the logistic regression is like doing linear regression on the log odds, and so that's where it comes from. But I'm not going to go into that. But there is a what can I say? There is a some thought behind it that makes sense. Oh yeah. So if you know linear regression and you can sit there and compute the log odds, then it is then that's a natural then the logistic regression model is a natural thing to arrive at. Okay.
I just add that they weren't mathematicians, but a number of social scientists and early machine learning people came across this idea. They called it a perceptron, but it was exactly this idea. You want to divide your data into two pieces, and they were trying to understand how the human brain worked and, discriminated. And that's so, they knew about logistic regression, but they were following that idea of, if I wanted to do something different, this is how I would do it.
Yeah, I mean it's been developed over many years, but I mean logistic regression is, I don't know, it's probably less than 100 years, maybe 100 years old, but it's not certainly not as old as linear regression. And linear regression is much older. But as I said in the beginning, it's classification is really where it's at nowadays. Most of the models in machine learning are deal with classification problems. Well, let me just finish up here and see what we get now that we have found the correct minimum. And now the model in fact does predict that the O-rings are damaged, and you can see here it gives us a probability of 0.999 that the O-rings would be damaged at a launch temperature of 31 degrees. So the model now is giving us the right prediction. So if we'd done this analysis before, because we had the data, and then maybe they would have been avoided. So let me just show how it works now. So if we look at the prediction over the training set with these values of the parameters, we get much better. Well, I didn't show what we got if we didn't use the old ones, but we get only 3 are misclassified. So the accuracy in the training set is about 87%. And finally, here is how we could actually find the correct minimum, because we can in fact just minimize this function using another algorithm. This is the algorithm here. It's called BFGS. Next time we'll talk about Newton's method, and that's BFGS is sort of a variant of Newton's method. So we use Newton's method, we get something that converges much faster and actually will converge to the right number. So it is possible. There are ways of more advanced ways than just doing gradient descent. They will give us the correct answer. So yeah. So I'll stop here. There was a long thing. So I hope I didn't take all of Adam's time away. So yeah. So that's it. Are there any more questions than what we're seeing?
Professor, this one question. So this loss functions for each of these regression models.
Yeah.
How does one come up with those, right? I mean, or they are like defined for a specific regression model? I mean, or there's a science behind it?
Yeah, it is. I mean, there is again, there is a theory behind this loss function. It's trying to minimize what's called or rather a distance between two probability distributions. Again, this is something called the Kullback-Leibler divergence. But there is so it does say there is a theory behind it, and I'm not. We can't really get into this because this is fairly advanced. But it's not something that comes out of nothing. It's not something that just got pulled out of the thin air. There is a reason behind it.
I guess like probably Tejas is asking when you use some libraries for doing linear regression or logistic regression, it automatically applies these loss functions, or do you have to write loss functions?
No, you don't have to write these loss. It will use these loss functions. So if you use the libraries, you use SK scikit-learn, right?
Yeah.
What we've seen. Then you just call a fit function. You take your let's see if I have a. So if you look at the code that I think I included that code in the code file I set up in the notebook I set up. You see that all you have to do is to put in you have to instantiate your model. So instantiate logistic regression. And then all you have to do is to use the fit function from that object, and that will automatically take the loss function and minimize it and give you a value. It will if you use scikit-learn and you try to do this experiment here, you in fact get the wrong value.
Okay, so I was going to ask that question, that if you use the library function, how would it know that where to start running the gradient descent? So it can also get wrong.
Well, it just takes a random.
Yeah.
It randomizes it, right? So it takes a random number and starts it there.
Right.
Takes a random point. So you have to put in some. You have to tell it a little bit of where to start. You can do that. You can instantiate your logistic regression object with parameters that tells it where to start. And so if you do the analysis and what we did here, then you will know that you should start at a different point. That you shouldn't start at just a random point. But that's what the algorithm will do. It won't know where to start, right? Because it has no idea where the minimum is. So it'll start at a random point, and then it'll try to find the minimum from there. So it's yeah. Again, you have to be careful. Always careful. It's not there's no free lunch here. Yep. Other questions? All right.
So just one final, sorry.
No, go ahead.
This fills me with a lot of paranoia if I ever use these things. And again, I'm not a mathematician, I'm not even a machine learning practitioner, but to those who are doing it, how do you, I mean, I know you said you have to be careful, but what does that mean? I mean, just look at it and look at test data and then look at it back again and just convince yourself that you're right?
Yeah, basically. I mean, you have to not just rely on the first answer you get. You have to. I mean, you have to do a back testing. You have to have a test set and a training set and try to estimate the errors you make. They will go a long way towards discovering if if there's sort of serious errors in your reasoning. Here, there's a very serious area, right? But you would, yeah. So in this case, we could sort of graph the loss function and get an idea that there was a serious problem. But it is a matter of looking always at how well does it perform, estimate the accuracy on the training set, have a test set and estimate the accuracy on the test set. And if you get very bad results there, then you should definitely think twice about using that model. And you might see, you'll have to check to see if there are things you can do to improve your estimates or improve your model. So
Niels, let me make a comment. So in case if the model is wrong, if you got the incorrect minima, then even the fit or the estimation for the training training data will also be very bad.
Yeah, right.
So that will be a big
very
sign.
bad. Yeah, yes, sure.
Probably doesn't have to be.
What's
Sorry, Adam?
I'm just saying probably it will be. It doesn't have to be. It can be.
it doesn't have to,
it
but
doesn't have to be. But
likely to happen.
I mean, you could be fooled for sure. But in this case, it would be. Now I didn't show it, but in this case, it would be. It would be very bad on the training set. You would have almost very very poor set there. So it would be pretty clear from doing that.
And also, it's not only possible in logistic regression. The same kind, if we get into, I'm just wondering, can we get into the same kind of situation in a high-dimensional linear regression that the gradient becomes like the contour curves have valleys and we
no, you can't do that because that's sort of I mean the loss function in linear regression is sort of symmetric, right? It's like that's like a bowl.
Yeah. Okay.
So here, so in that case, it's if you look at the slices of the loss function, they'll look almost all will look the same. Here they look very different, right? And one slice, it goes down in a very sharp point, and in the other direction, it goes almost in a horizontal line. But for the square loss function, you won't have that. You just sort of see a bowl shape for all the slices. So you wouldn't have that bad a problem in linear regression. Linear regression, there's also there's a closed form solution to it. So you can by inverting some huge matrix, you can actually find the exact solution to the minimum. So yeah.
I would just like to add two comments. Firstly, with regard to loss functions, this is something that people think about and have thought about, and we have the advantage of in 2018. There's a lot of empirical knowledge of what are good loss functions, as well as theoretical knowledge. And when you build these models, almost all the functions have a standard set of choices for the loss function, as well as the ability, if you have some idea of what a new and improved loss function ought to be, for you to say, use my loss function in it. And the issue of convergence is can be very serious in these things, but at least, if you tell Python or R or anything, run a linear model, it assumes you want to use the ordinary squared loss function. If you want to use absolute value, you can. You just have to tell it. And and for classification problems, the same thing is true. There's a standard set that experience has shown. There's a standard set of loss functions that experience has shown are useful. And if you read the documentation for the function, you'll discover what they are, and you can try all of them. The other thing is as I said before, when you're building these models, you don't just, building a model isn't like the end. It's not like I built the model, I'm done. It's just the first phase. And the real serious number you want to know is whatever your loss function is, how well will this model work on new data as measured by your loss function? And so in any sort of so Neil's lecture was step one. I'm going to take the same data and I'm going to deal with it in a a more sophisticated way where we can get some idea that how well the model works. So it's a great point to mention that how can I be confident? And the answer is you can have high confidence by using standard techniques that we'll explore now or next.
Yeah, let's see it.
All right, so should I take over?
Yes,
Yep.
please.
Okay. Yeah, this is, okay. Let me just, so the challenges, so I picked this title, I didn't use correct capitalization, but given the questions we have, I think this is the right title, The Challenges of the Challenger Dataset. So I did this in R, and I downloaded the data from the UC Irvine Machine Lab data laboratory. They have a lot of data sets, and so just I'm not going to present you with immediately a clean data set, but notice for reproducibility, I get the same answers every time because I've set the seed, and then I just read this data set from my library. And the first thing I want to do is look at it, and I have no idea what that means. And I have no idea, the summary doesn't help. But in this case, the UCI site was explained exactly what was going on. And I actually only want variables 2 or 3, which is whether it failed or not and what the temperature was. As Neil was saying, you have to look at your data set. So is there anything going on? So the first thing I wanted to do is I coded it as 0.